Are you ready to go, Peter?
Yes, I'm absolutely ready to go.
Well, in that case, take it away.
Okay, I'm calling this talk Iterative and Recursive, but I'm using these words in a slightly different way to the way they're normally used. But they're connected. It's not completely unconnected with the normal way. And I'm really going to do a bit of a historical progress through my own journey. I'm trying to get an ever more fundamental theory, and I'll show you how to do it. We had some talks in our previous conference on laws of form about such things, and I want to show you this way of doing it that I've come up with myself. And I want to find a recursive insight which covers many things at once. And largely by recursive, that's what I mean. You have an idea and everything will come out of it. You get multiple answers immediately. And where it's not possible, we have to drag it out with iterative processes, the next stage and the next stage. Now, I think nature's method is to be recursive, because it has to deal with the universe all the time, now. So it's basically a recursive thing, nature. However, we're not very good at that. We're painfully iterative the way we do it. And this is what we call the scientific method. And everybody's taught to think this way. And it's not the best way of thinking, but it's the easiest way to teach people how to think. But what I'm interested in, what I've done, is the few instances where I've had what I consider a recursive breakthrough. And sometimes, when you've done that, all the iterative dogging that you've done can actually make some sense within the new pattern. And then we can make comparisons. And this is a favourite diagram of mine. And if you look to the left, that's where everything's coming from. And this is where I'm looking. That's where I'm trying to get the next stage of this. And on the right is all the iterative way of thinking. Not that I'm against iterative, that most of science needs to be done that way, but if we're trying to get to fundamental ideas, we don't want complex ones. Complexity comes from entangling simple ideas, and we want the simple ideas, we don't want the complex ones. And so all this nonsense about unifying general relativity and quantum mechanics out of the window. We don't want to do that kind of thing. It's a bad way to proceed. Nature isn't a clever mathematician. Nature is the simplest mathematics it can ever do. Mostly based on symmetry. It doesn't want something immensely clever. If it's clever, then it's wrong. Well, it's not wrong. It's not nature anyway. I also say nature couldn't be so stupid as to be so clever. So I want to always find a recursion if I have, and I think I've found 3 that really would pass that test. But you can't derive these things, it's the whole point. You've got to somehow have that moment of intuitive insight which gives it you from whatever you've done before. And then, so whatever you derive is built into what you already had. So you've already got an iterative development, and then you say, I know what explains all this stuff. But you want to open massive new possibilities. You want to get new things that couldn't have been part of what you've done before. So, as I say, you've got to intuit it. You can't actually work it out. There's no method of doing it. And this is why it doesn't feature in scientific education and training. And it's frequently never mentioned. We're not trained that way. But, so how am I going to start? Well, I'm going back a long, long way, more than 40 years, to the 1970s. And this was my first idea of this kind, and I think it's really, in many ways, is the best one, because it's from that everything else eventually developed. And I can't tell you how I got this idea. Lots of things went into it. But as we were talking about Spencer Brown and zero and stuff recently, I say one of the key things was that nature couldn't be restricted by characterization. So you can't say nature has this character or that character. And I think one of the things it isn't is discrete. Though discreteness is important, nature is not discrete, nor is it continuous. It doesn't have any character. And effectively it's a totality zero. And if you start with a totality zero, There's no other idea you can have which you cannot explain. You've got to have an idea you can't explain as your starting point and your end point. If there's an idea you can explain, then you've got to explain it. It's not fundamental. And then, of course, there's dimensional analysis, which everyone does, which is a very important thing, and it's often glossed over as merely a useful mnemonic, a useful tool, but I think it's much more important than that. It's telling you what the fundamental things are. Why does it work? I mean, we usually use space-time and mass. The Victorians had electromagnetic theory, but they never included charge. And the reason why they didn't is because the system was closed once you included charge. So you didn't need to actually specify that separately. And the realization many fundamental laws of physics are just relationships between abstractions. They don't tell us anything directly about the world at all. They're just relationships between abstractions, which then we apply, but they're not actually anything to do with the world. And the conviction that Hamilton's quaternions are the only possible explanation for three-dimensionality. It's so obvious this man discovered this three-dimensional structure which was unique and perfect, and there was no need then to pretend that we couldn't explain three-dimensionality or three-dimensional space. Of course we can. And this is what I eventually got. This is my structure, and that's one diagram, and this diagram was actually not drawn by me, but it was drawn to my specification. I'm not particularly good at drawing, and it's a category theory diagram, if you like.
Plenty of commuting triangles.
Do you think that's a category theory diagram? It could be anyway. It looks like one, and you see there's three fundamental dualities there. Each of these four objects has a duality, has three dualities. Three things that it's either one thing or it's dual. And I found that those things were absolutely dual. They were perfect symmetries, all of them. And charge now isn't charge as in electrical charge. It's all gauge theories. It includes strong and weak as well. Now, many people would say they're different things, but this was prior to grand unification ideas. And then, very soon after, we started hearing about those. And those ideas suggested that both three charges under the right conditions would be perfectly symmetrical. And mass is, of course, not discrete mass, it's mass in a more general sense, mass energy. And I am one of the people who stand up and say I prefer relativistic mass. I don't like this idea of using mass only to mean discrete mass. And that's a more diagrammatic, more textual way of writing it. And what I found was that the only continuous things in the world were non-dimensional or one-dimensional, and the only discrete things were three-dimensional. Discreteness is purely three-dimensional, purely anti-commutative. It's got nothing to do with anything else. There's no other source of discreteness in the universe other than three-dimensionality or discreteness, or anti-commutativity. And imaginary charge, well, that's simply the opposite to real mass, because that gives us opposite laws of attraction and repulsion. And you can write those algebraically, and that's a conceptual zero. So I've got conceptual zero. And if these are the four parameters that we do all physics with, well, we don't need anything else. This is it. All I've got to do is show that this is it. And you can do all kinds of things with that group. It's an abelian group. Every element is an identity. No element's better than any other in the group. Any can be the identity. Each is its own inverse, and you can represent the binary operation in that way.
What do you mean every element is the identity?
Well, you can rearrange the...
Squares to the identity.
No, it is the identity.
But-
Well,
but-
no, it's the identity element, I mean.
Well, but an identity element would multiply everybody else.
That's right,
and
it
not
does.
change it, and not change.
That's right, it does.
And that would mean that the multiplication table would be just,
Commutative.
nothing.
No,
going.
you can arrange it. You see these x, y, and z. If I take x, y, and z as the identity in that table, then I can do those multiplication
Oh, you
rules.
mean you take that table and then you say, I shall have that X is the identity, and
Yeah.
then you will get a Klein for
Well,
it.
yeah, whatever, I get
Or
Klein
Y,
for.
Or,
Yeah.
yeah.
And so, but I can do that with any of them. I can do that, I can rearrange the letters and the signs so any of them are anything.
Okay, so we're talking about the positive identity as well.
Yeah,
Yeah,
but
good.
I can change mass to minus and time to plus. It doesn't matter, it's arbitrary. It's an arbitrary choice that I've made
So you
algebraically.
then have minus x times minus x is minus x.
You can do that.
Yes.
Yes, I've done that as well.
Okay.
You can do anything.
Good.
You can do virtually any trick you want like that.
So you're saying there's algebraic freedom to do that?
Yeah, there's a lot of algebraic freedom.
Yeah, I'm still a little confused. Let's take the multiplications that you had in the previous. There you go. Now you, no, the next one. No, that one, stop. Now, you have x times, you've written x times x equals x, but if it's a group, then x has an inverse and you multiply.
It does.
And you can get.
Each is its own inverse.
The only x such that x times x equals x in a group is the identity.
Yeah.
So that's what you're saying.
Yes.
You could decide that x times x is x.
Yeah.
And then take the consequences for y and so.
Yeah, correct. But I can make any of the parameters do that. I can rearrange the algebra so any of them does it.
But can you make all of them do that at the same
No.
time? No. Any
You're
one.
up to
Any
make
one.
a
Yeah,
choice.
that's what I was saying.
Yeah, any one.
Yes.
Yes.
Okay.
And that's the one with mass as the identity.
Yes, I see. Okay, right.
And you can see this group contains two major subsymmetries, if you like, duality and anti-commutativity.
So
Three-dimensionality.
is this like when we're doing quantum mechanics and we decide that mass is a simple operator and the other two are derivatives?
Yeah, sure. You can
Yeah,
do
that's
it.
the same kind.
Yeah, you can make any choice you want.
Yeah.
You've got to make a choice, but you can make any. Okay. Now it's very important that there are two subsymmetries, duality, and you can see duality everywhere because of all those things. They're dual, and the duality is all the way through it. And of course, anti-commutativity, because two of them are three-dimensional. And basically, 2 and 3 seem to be the only really important numbers in nature. Everything is based on, well, I mean, that's an exaggeration, of course. They're only important integers in nature. Everything else is based on them. All other integers that appear in nature are based on, that in symmetries and so on, seem to be 2s and 3s. I'll show you that later. So, the perfection of the symmetry structure is character of a recursion, as I describe it. And I've looked at it for 40 years and I know it's exact. And it's all the more convincing that itself can be mapped onto 3 dimensions and 3-dimensional structures and quaternions and things like that. This can be mapped onto double quaternions. Or not so much double quaternions as the double algebra that you can get from double quaternions. But it's mappable onto that, and something, it's like something cyclic in it. You get 3-dimensionality, you put it back in and rearrange the stuff in a 3-dimensional way. It doesn't privilege any of the 4 group members, though nature does privilege space because it's the only one you can measure. And so each parameter is its own inverse. Each can be the identity element, and it's also abelian. And I get some nice pictures of that. That those, if you look at those circles, each circle has 3 colours, primary or secondary. You can do it either way around, and each has a primary or secondary colour. Primary for one property, secondary for its anti-property. And you can do the circles, and this inner circle could be mass, or it could be space. You can do any of the ones you want. You can do
Is
it
there
anyway.
something significant in the fact that the group itself, the Klein group, doesn't privilege any of the elements, but nature does make a choice.
Makes a choice with space, yes. And we know why now. We don't know why from this theory, but we do know why later.
Sorry, I got totally lost. What was this? What's this colour diagram?
Well, if you look at the inner circle, let's call that mass. What property does mass have? Mass is a continuum, so let's take it as the magenta, as the green colour.
Oh, okay.
And the blue colour then will be another property, say, it's real nature. It squares to a positive number. And the red one would be, what's the third one that we haven't done? The conserved nature. And then the next parameter, you can work out what the next parameter has to be. What did I say the blue was? That was the real nature. Was it the real nature?
Yeah.
So the other real one is charge. So this one is charge.
So you've got two. So which are you looking at now? You've got two.
Sorry, I'm not pointing. I need to point to the diagram.
Yeah.
Okay, so this is mass. That's the real property of mass, arbitrarily chosen. Could be anything. So that's the real property of another parameter. So that one is space. So this circle now must be space because it has the same real property as mass. If I choose now that to be the conserved quantity of mass, yep. This is the fact that space is a non-conserved quantity.
So it breaks up into 3 domains.
Yeah, 3 domains. There's three dualities. And it has to go either side of the duality for each property. And so once you've picked out one, all the rest are automatic.
They're determined.
Okay.
So you take one as your identity. So you take, for example, green central is your identity.
Yeah.
Yeah, and then everything else follows
Yeah.
from that.
But I could have chosen a different parameter,
You could have
and
done
different
that, and then you
representation, and I could have chosen secondary colours.
Yes. But they always have that form.
Yeah, so it's a perfect form.
Yeah.
Yeah.
Okay, with you.
So that's why it's a perfect symmetry.
So the 4 levels are the
4 parameters.
Are the mass, yeah, right.
Yeah.
Charge, space, time.
And that's, if you sum them up, you get white, so you get, as it were, 0, no colour.
Yeah.
And this is a 3-dimensional representation, and the red lines are the, for example, you can always choose them to be different. So this is why I'm saying it maps onto 3-dimensionality. We can draw a cube in which the red lines go to 4 of the 8 corners. You can see 4 red lines, they're going to 4 of the 8 corners, and those would represent X, Y, Z on the chart. If we go back here, these can be considered Cartesian coordinates for these parameters. And so we point to 4 different corners of the cube from the centre. If that's 0, and then we get X, Y, and Z axes for the cube, then we can use Cartesian coordinates. Like,
Is each corner a parameter?
yeah,
The edges
yeah,
are.
Edges are.
yeah,
The edges, yeah.
yeah. No, the red line is. The red line represents the parameter going in the direction X, Y,
Okay.
plus X, plus Y, plus Z.
And what's the significance of the shared corner?
I'm sorry?
They share a corner, the blue and the...
It shouldn't. The blue is this
The
corner.
centre is zero.
Sorry, the blue is this corner.
You need to-
It's not easy to see. Actually, I've got one without the cube, without the grid lines, so that would be easier.
Yeah, that's better.
Yeah.
Yeah. Now you see this one here, the blue comes here. Yeah, the blue goes there.
Yeah.
Not there. The red one goes there. And this. You were asking about if I chose minus X instead of X. Well, that's what would happen with the blue ones. This is the alternative way of representing them. This is what I call the dual group.
The faces are the colours. The faces are the colours, yeah.
No, there's no faces. There's no colours on the faces. The lines are the. Oh, sorry. The faces. Yeah, the faces
If I want to
are.
map it from your previous
Oh,
diagram.
from the
to
previous diagram, they would be. Yes.
Yeah, the faces would be the colours.
Yeah. And then this is another diagram, tetrahedral, and you can take either the colours or the primary colours or the secondary colours to be property, anti-property, and you can take the faces of the tetrahedron to be the 4 parameters. So that's another way. But you see how it builds back into 3-dimensionality. It's structured into 3-dimensionality as well.
You're going to share these slides with us?
Oh, you can have them, yeah. Now, when I first did this, I just found a lot of things were obvious from it. A lot of things, if you believe this to be true, then a lot of things are obvious. Obviously, conservation laws of mass and charge are obvious because, you know, that we start off with them being conserved quantities. Noether's theorem is obvious because you've got conserved quantities and non-conserved paired off. Gauge invariance is obvious, that's a part of non-conservation. Same with translation and rotation symmetry. Lepton and bearing conservation are due to the fact that the charges, if they're truly conserved, then the dimensions of the charge, the three different ones, are conserved as well, and you can't swap one for another. And a lot of people are going wrong in particle physics because they're trying to do that. They're trying to show the proton can decay. Well, it can't. Because if it could, then you could rotate those three axes of charge. The electric strong and weak could rotate into each other, and they don't. Nor can they. Nor can they ever. Irreversible in time, that's because it's continuous, because it's one-dimensional. Unipolar mass, because it's one-dimensional. Why light charge is repelled, but masses attract, because charges are imaginary and masses are real. Anti-states, because you can't have imaginary numbers or quaternions or anything like that without the also pairing them with the plus and minus. What you can have real numbers that aren't paired. Again, this is a really subtle one. I didn't even know this mathematics existed when I did this, but I realised that space had to be real numbers, but somehow discrete. A non-conserved discreteness, so you could keep changing the discreteness. And I found that it was, there was a mathematics that I didn't know existed. Non-standard analysis. And so basically mathematics is either out there or we construct it. If we construct it, it's non-standard. If it's out there, it's standard. I don't want to go into it, but Zeno's paradox and the irreversibility paradox are obvious consequences of mass and time, space and time representations. And again, why can we have inertia and gravity for mass, but only we can only measure charges if there's another charge? Whereas we can identify mass without another mass. That's because mass is real and charge is imaginary.
So, Peter, what do you mean by discreteness when you use
I know we've discussed this many times.
Well, what I mean is, could you summarize again just the point about discreteness and three-dimensionality being interlocked?
Well, what I mean is that the two parameters that are discrete are also three-dimensional, and I can't see any discreteness in the others. And if everything comes from those, then it must be from that.
I think I can explain it.
Oh, well, I can go into that in a later theory, but this theory at the moment is all I'm talking about. And charges being point-like because they're conserved, and that we can count them. They're countable. And there we are. That's discreteness. Don't come. These aren't iterative. They're just all automatically part of the explanation. There's no explaining. And it is purely from symmetry. And a lot of ink has been spilled over these, but to me it's a total waste of time. Because you can explain them in 1 second. Anyway, sorry about that.
No, not at all.
But I published a whole book in 1991 showing how to derive iterative consequences from these. And some are straightforward, but some aren't. So a quaternion requires a fourth scalar component. And if we got 4 parameters only, and we got one is a quaternion charge, then the real one that goes with it is the mass. So that suggests a numerical connection between those units. By symmetry, vector space requires an imaginary one to complete it. Pseudo-scalar fourth component, of which only time is available, leading that mean we must have a connection between them. And again, from the group structure, every parameter has a direct numerical relationship with every other, and it must have one with its own inverse. That's why we have fundamental constants connecting them. We can also write down relations between different parameters, inverses, construct new composite parameters, and bring in conserved and non-conserved. That's where differentials come in. There's a lot of discussion about that in various forms. We have to set That's one of the things that makes a thing non-conserved, that we can't actually write down a value for it. We can only write down the differential. We can only say that it changes. And so we can introduce the properties containing the group to extend our equation, vectors, squaring of imaginary term, space-time connection, all that sort of thing. And I don't want to go into any of those details today, but I have done it many times. We also get an intrinsic relation between relativity and quantum theory, special relativity values. Deriving one means you've got to have the other. It's not as obvious how to do quantum mechanics from this thing. It's a lot more difficult. But it's clear that you can do it, and that the basis of the concept of uncertainty is in the concept of non-conservation. If a thing isn't conserved, then you can't pin it down. I can give far more discussion about that. I haven't got no time today, because I want to go on to something else. And again, I mentioned earlier that the three charges have to be in some way, in some regime, identical in effect. And so it's believed they are at grand unification. Also, each has a Coulomb component. None of the four forces is without a Coulomb component. And that, to me, is what is left at grand unification. I'll talk about it later. The non-standard analysis was an unexpected consequence, and I didn't know it existed, but I eventually found it did. I'm not a mathematician, so I didn't know this automatically. And it struck me that this was the exact mathematics I needed. And the fact that the space 3D had to be exactly symmetrical to the charge, and we were taught vector theories, we had the vector product, the scalar product, and you just learnt them, and that's what you did. However, more modern ways of thinking, based on older ways of thinking, like Clifford algebra, says that you cannot have a vector that has just a vector product or a scalar product, it has to have both at the same time. And both at the same time is in fact an exact parallel to quaternions. And eventually we learn that the vectors, the real vectors, are just imaginary quaternions. Quaternions complexified. And Hestener's school called these multivariate vectors, and they showed that it automatically included spin. And again, this is quite a different development. I took the idea of continuous mass seriously. And this is certainly true after we have discovered the Higgs field, which meant we had to have a new relation between gravity and inertia. And I was doing this in the 1970s, then again in the 1990s. And I got from this, I got a prediction of dark matter at 67% of the universe, currently 68%, before they actually discovered dark matter. It's now 68%, so I'm winning on that one. I found a fascinating extension of Noether's theorem. The versions of Noether's theorem that I used. For example, you could extend Noether's theorem by symmetry, so it wasn't just energy and time and momentum and space. What you could do is say, what about charge? So you could do mass and energy, easy, because we have relativity, so mass and energy. And so mass and time, yes, okay. But what about charge and something? By symmetry, you have to have charge and momentum, or charge and angular momentum. Charge and momentum for linear, for the for the amount of charge, translation, but the rotation of the charge is angular momentum. So I came to the conclusion that the fact that the charges could not rotate into each other had to be the same as the conservation of angular momentum. And I hadn't a clue how to do that mathematically. It just had to be true from the symmetry, it just had to be true. Eventually I found out how to do it. The conservation of angular momentum, as gyroscopes will tell us, is not one law but three. It's the conservation of the magnitude, the direction and the handedness. Are three separate things, that no connection between them, they're all separate. But they all go into angular momentum. And here we can identify each one of these with one of these charges. Strong charge for direction, weak charge for handedness, and magnitude is all three, but the only one that it's only is electric. And ultimately that gives us our SU3, SU2 and U1, as I can show. But I don't want to do it now.
Wait a minute, which way are you putting it? You're putting the electromagnetic one's 3?
No,
the electromagnetic
it's
one
one.
must be 1. Yeah, good.
you won.
Yeah.
And that would explain why proton decay wouldn't happen.
The conservation of those separate charges is why proton decay doesn't happen, and it's why you get lepton and barium conservation. So, I studied three-dimensional systems, and I wrote an ANPA paper about it, and I found there were two types. There's a non-conserved type, corresponding with space, and a rotation symmetry is preserved, and a conserved type relating to the characteristics of angular momentum. Now I know there's an aspect of angular momentum which is space, but the other aspect, in which there are three types, the rotation symmetry between those three concepts is not preserved. You can't rotate those concepts. Then I got particles in a strange way. I thought this has to derive particles. I don't know how to do it. And I took the three charge side variations and tried to identify. I got the idea that quaternions are rotation symmetric, but charges are not. So how do we do that? I can't really go into the detail, but I got these sort of tables. And the interesting thing about those tables, if you look at the middle, the second row of each, so the second row of this, that's a second row there, and you'll see that there are three of these, and you see that the strong charge bit on the second row rotates, except in the fourth one. And the first three I identified as the three quarks, and the fourth as the leptons. But that's putting them all together without the bottom ones. And
So
then
you're saying this is like a rotating vector that identifies all these particles to these...
yeah, I have got a rotating vector version, but I've not got it in this presentation. But I've got other versions later. I've got better versions, but this is my first version. And that's what I got for the charge structures for these. And what really interested me was how these things here, sorry, it was the weak one that had a variation in sign. And this was where this business of strangeness and stuff came in. But I don't want to go into that.
And do your tables tell you how the particle interactions work out?
Yeah, they do. But I've done better since, but this is what I had then. And this is very interesting. This is really interesting, the Mezzo Octet. Because if you look at that, the really one of interest is K. Because the K, it can be either 0 weak charge or 2W or minus 2W. And I thought this is interesting because K is the one that's CP violating. And I came up with an explanation of that later, but I'm not going to deal with that either. That I've got to leave lots of things out. So CP violation in K. Neutrinos second and third generation each have a charge structure W. So that's got to be interesting, that there's no distinction in the charge structure between second and third generation neutrinos. And I think that is a preferred decay, a preferred, when they're talking about neutrino mixing, that is a preferred mixing for the second and third generation. Mix virtually out at 100%. And that to me is the reason why. Because they've basically got the same charge structure. I also got granularification at the Planck mass. Now this is really remarkable. I also think that the switching of the S charge was a prediction of the EMC effect, which was discovered partly by my colleagues, and that was that the proton spin was not derived from the spin of the three components, because basically in my version the strong charge carried the proton spin. It was it was like a momentum which carried the proton spin.
Wait a minute, Liverpool wasn't in the EMC, was it?
Yeah.
Or is it? Okay.
Yeah, 1989, 1987.
Oh, they joined later.
No, they weren't. No, they weren't. My colleague who shares my office, Jeff Court, was often talks about
Jeff Court, I know. Yeah, okay.
it. Yeah, he was in it. Yeah.
Okay. Right, I've just forgotten. Yes, it was on. Anyway.
What I'm interested in is that, as far as I'm concerned, the third charges for quarks came from the gauge invariance of strong interaction. There's no third charges in reality. They're just seem to be third charges because you've got perfectly gauge invariant thing between three things.
And that's where the rotating vector part comes in.
That's what my rotating vector did. And I noticed that other people have worked on this, Fury, Dixon, many others, worked on, not one of them has found a natural way of deriving 3 or thirds or 2/3. Anyway, so the main criterion for establishing if these true is whether they correspond with nature. But if they are true, then we expect to get a better recursion with it. So I got a second recursion by the algebra of the Dirac equation. And I would now call that the algebra of physics, even the algebra of nature, because I've also found it works in biology and other areas. And this was first published in 1994. And this came from the separate algebra structures associated with the parameters. I glossed over that when I wrote the group down, but that's the algebraic structures for the 4 parameters. And in fact, you can actually see that their physical properties are simply algebraic properties. They come from those algebras. So that's all they are, they're just algebras. And what's very important is that if you've got quaternion for charge and a pseudo-scale for time and a scalar for mass, then when you put those together, they're equivalent to another space. So this algebra is like having 2 spaces. Now when I put this algebra together, took a tensor product, I found it was exactly the Dirac algebra, corresponding perfectly with it. And so it's as though we've got 2 spaces, the red one and the blue one. So this turns out to be exactly the same as the Dirac algebra. You can do it term by term, no problem. And there are 64 units in the Dirac algebra, counting plus and minus, but the equation only needs 5. So the interesting thing is that these 5 are generators of the Dirac algebra, the whole algebra. So if you've got those 5, you've got the whole algebra. So in a sense, those 5 give you everything. And the algebra is sufficient to include 12 different versions at the same time. There we are. So that's the Dirac algebra as I would write it. And if you take any line of this, especially the first line is the one I normally use, but you could use any of them, you would get a version of the 5 gamma matrices of the Dirac algebra. But I think it's important that gamma 5, which is here is the J, is included at the same basis as the others. So how do we construct these generators? Let's see what we do physically. We've got the charge units, IJK, quaternions, and I say let's just imagine we distribute them onto the other units, and we'll get these composite units here, these composite units. This is your gamma 0, this is your gamma 1, 2, 3, and that's your gamma 5. And essentially you've created a new physical concept, a new physical quantity. You're actually creating energy, the concept of energy from space, time, mass and charge. You're creating the concept of momentum. You're creating the concept of rest mass, discrete mass, which you didn't have before. You're creating entirely new, and these are quantized concepts because charge is quantized. And very importantly, you've got to break the symmetry of one of those 3-dimensional units. You've got to break the symmetry to make it work as a generator for the group. And so I say it looks like the result we found in the Noether theorem. The fact that you've broken the symmetry between one of the 2 3-dimensionalities. This is why it's broken. It's not fundamentally broken, it's broken when we entangle all the objects together.
And what it looks like unbroken is the parameter group.
Yeah. The basic group is unbroken. This is entanglement of the parameters. And we see the reason why we've broken the symmetry between the 3 charges. Now let's put it together. If I put those together, now in this object here, in the bracket, the EP and M terms are just scalars. They're just multiples, they're not actual fundamental things. The physical identity of the object is determined by the algebraic operator in front of them. So IK is what is really energy. E is just a scalar value. Hi, John.
Hi.
I and so on is the first term in the momentum, and px is just a scalar value, and J is really mass. And if we square that,
Sorry.
if we square that, we get Einstein's energy momentum mass equation, E squared minus P squared minus M squared, or if we want to put in the C's, we get that. And this changes our whole value of our whole understanding of what we mean by it. The Dirac equation is simply quantizing this nilpotent equation. It tells us things about the Dirac equation that's not obvious in the conventional version. In the conventional version, we got these arbitrary objects coming from nowhere, which we bang into the equation to make it actually work. But this is a slightly different version from the conventional version. It's as though we'd multiplied the whole conventional version from the left by gamma 5. If you do that, gamma naught doesn't change, gamma doesn't change except to a different matrix representation, but still gamma naught, gamma and gamma. But gamma 5 appears on the mass term. And we've now got a much more symmetrical equation than we started with. And if we quantize this, what we get is a nilpotent amplitude or wave function that squares to 0. And now we just derive laws of physics from this algebra. We don't need to go through any process to do it. It just comes from the algebra. Quantum mechanics, special relativity, classical mechanics, we will do that just from the algebra. And
That was a better way, right?
well, this is a better way because it's more recursive.
Instead of going through the original parameter group, you're now going through
Yeah,
the rock out.
But without the parameter group, we wouldn't have got here. But they're both two aspects of it. One is when they're not entangled, the second one is when they are. And if we write down a Dirac equation of point-like particle in the field of another, Coulomb potential is necessary, as we can show. And once we got a Coulomb potential, we got a great deal of physics. The top expression is really the Dirac formulation of how to put the del operator into polar coordinates. The only thing that's different is that this, he doesn't quite make it as explicit as this, and he kind of fiddles it, because this is an ordinary eye, but when he does it, it's equivalent to a quaternion. Though he doesn't actually say that, it's equivalent to a quaternion. And you know, John and me have discussed this as
At that stage you didn't know it.
a fundamental aspect. And if we stick that into the operator like that, and then say, okay, I want a nilpotent solution of this. The way to do this is we don't bother with an equation, we just have an operator expressing the particle state. And then we put in a phase of some sort. And it operates on a phase of some sort, but we've got to choose that phase in such a way as we get a nilpotent solution. An amplitude comes out, an eigenvalue that's nilpotent. Now, you cannot do that for this as it stands. It will not give a nilpotent solution. If we're talking about polar coordinates, a point-like particle in the field of another point-like particle, we can't do it.
There is a way.
Oh no, but there is a way.
Good, yes.
You can't do it unless there is a Coulomb term in there.
You need a yes, almost. Anyway, yeah,
Anyway,
very
we'll
close.
talk about it later.
Yeah, I'll show you a picture, it's lovely.
Yeah.
But yes, you're right.
You have to compensate
Yeah,
it.
you do, yeah.
You have to compensate for this,
Yeah.
because it will never square to 0 unless you got one in there as well.
Did you make that up or did you get it from somewhere?
I worked it out.
Good man. Hey!
I worked out I couldn't do it unless I put it.
Nice.
So
Impressive.
simply putting a particle in anywhere near another point particle,
Yeah.
it gives you a Coulomb term.
Yeah.
So the universality of the Coulomb term is explained. That's why I've already explained that. Yeah. So a lot of results follow, and I haven't got any time to do them, which is because, I mean, you're talking about 40, 50 years of development, there's all kinds of stuff. So I'm saying we don't need an equation, we only need an operator. Once you define it, then it's like the general, you know, with a chest full of medals, and somebody said, where did all those medals come from? And he said, I got the first by accident and the rest followed automatically. So essentially, we get the first by accident or some means, and the rest follows automatically. We get our operator, and the rest follows automatically. And that suits me, because I don't think nature deals in equations. It doesn't deal in equations. Equations are our way of dealing with it. It doesn't say, I need the something or other equation to do this.
I'm going to do nature works on calculus, everybody knows that. God's doing maths.
And so, once we've defined the operator, everything follows automatically. The ultimate meaning is that each nilpotent provides its connection immediately to the rest of the universe, which will fit in with a lot of things that were said last week. The universe is its mirror image, and together the nilpotent object and universe sum and multiply to 0. So F for the fermion, minus F for the universe, F times minus F equals 0, F plus minus F equals 0. Yeah. And you can work it out that you get the same results as the iterative ones. And of course this is symmetry breaking. When I do that arrangement there, I'm breaking the symmetry of the red objects. But as a point of interest, the only other way you can get 5 generators for this group is by having 2 pairs of vectors or 2 pairs of quaternions, or 1 pair of vector and 1 pair of quaternions, plus imaginary I. If we don't get imaginary I with it, it doesn't work. But in principle, this is what Majorana does, something like that. But he doesn't believe in the imaginary unit. But if you do that, then you don't preserve your symmetry of your 3-dimensional space.
If you do it the other way.
If you do it the Majorana way, yeah.
You don't preserve the 3-dimensional symmetry
But
of your space.
he just has 2 pairs of vectors basically. But if you have 2 pairs of vectors plus imaginary number, you can do it. You can generate the algebra. There's loads of iterative consequences. It's very easy to do spin 1, spin 0, bosons, baryons, vacuum, CPT, creation annihilation, local and non-local. Local and non-local is dead easy, because local and non-local, inside the bracket's local. That's the Einstein bit. Multiply by another bracket, add another bracket, non-local. SUSY is automatic without extra particles, very easy that. If anybody's interested, I'll show them. And I get exact single particle solutions for electric weak and strong interactions. And the last 2 have not been done before. The electric one, I get, is the Coulomb term, the Coulomb expression, the hydrogen atom if you like. Well, most books take 6 or 8 pages. This takes 6 lines. It's that easy. Again, you get odd things and you think, can these be true? Can these be true? So, again, the entire information about fermion is contained only in the instantaneous direction of its spin and not anywhere else. It's not the value, it's not the magnitude, nothing to do with the angular momentum, it's just the direction. That gives all the information. And the same information is found in both spaces, the real one and the other one, which I call vacuum space. These are interchangeable. There we are, there's the 2 spaces. That's showing Pauli exclusion in the 2 spaces. If you do anti-symmetric wave functions, you get the real space. If you do nilpotency, you get the vacuum space. Standard model fermions, how are we going to do them? Well, that's a lot easier now. We just do something like that. We can pick out from the 64 units all the ones with quaternions, and we can match them against the algebra. Or we can do it that way, or we can do it that way. That's all. That sign is meant to represent all, and that's the choice of the quark. Which quark we're choosing. So, but what explains all this? There's always the next point and the next point.
That's what we're going to work out over supper.
Okay. Now, unfortunately, I did this next bit with a colleague who's now dead, so I dedicate this to him, Bernard Dyers. He was a computer scientist, and we first published it in 2002. So how do we explain where all this comes from? Well, he was interested in finding a kind of logic that nature might use, a rewrite system, as he calls it, without a fixed alphabet. And Chomsky and others have stated that you need, for a digital computer program, you need alphabet rewrite rules, start and stop. And that's just a syntactic program, but we don't want a syntactic, we want a semantic. And this is an explanation about an example of how to do it. We have two rules, A goes to B, B goes to A. Interestingly, that's quaternions in the plane. I goes to J, J goes to, well, yeah, IJ, just OK. There's no third dimension. And to me, that's why it generates Fibonacci numbers, because effectively you are doing a logarithmic spiral in the plane. So would nature's programming system resemble this? Well, I can't go into the detail of this, but all I want to say is that we did get this thing called a universal write-rewrite system, in which we had started with a 0 alphabet, and it just extended itself every time, and I've got no time to do this, so I'm sorry, I'm going to go shoot through it.
Did the return come after 4?
Sorry?
You're generating and you're forming.
Yeah, you can do it to infinity.
After 4. Can you do it at 4? Or does it happen at 4?
I'm sorry?
Does return come after 4? If you have a change, then a change. Then
No,
a
we
change,
don't
then
return.
you come to return.
Except in physics you do.
Yes,
you don't
exactly.
in mathematics. In physics you do.
Yeah.
And so effectively this is, if I make them algebraic, which I can do once I've shown that I can get algebra from this,
Yes.
I don't assume algebra, once I've shown I can get algebra from it, I make them algebraic. And so that's a example of how this works in effect. And the last one is basically where physics comes in. And the reason why physics stops there is because it can zero things at that point. And the idea is always to get 0. But the key thing is that we've got duality and we've got anti-commutativity. What duality is at every point, and anti-commutativity is where we got the i's and j's together. And it's as though duality and anti-commutativity are competing aspects in nature. Duality forces a conservative constraint on what we can do. Anti-commutativity forces us into newness, but in a constrained way, constrained by the dualities.
It's a question of where the nilpotence comes, at which level.
That level, that
Yeah.
stop there on that. But you see dot, 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 because you can carry on. For a mathematical structure.
In the mathematics, yes. But in
Yeah,
physics,
but not in
no.
physics, no.
Yes.
And not in other things as well.
No, that's right.
Because at that point you can get a zeroing.
Yeah.
So when you say at that point that you've reached the first particle, first fermion,
Yeah, that's basically the first fermion would be that point. But it doesn't have to be a fermion, it could be something else, as I'll explain. So duality and anti-commutativity are like competing symmetries in the aspects of the whole of nature. And one is a conservative constraint, and the other one forces into newness, though it is constrained because of the other one. And everywhere we see the numbers 2 and 3. Thank you. It's because of that. And if you ever get 5, you've got broken symmetry. Everywhere's 5 is broken. It's basically a Clifford algebra. Let's go past all this. And we've successively defined the 4 algebras we need for physics at the foundational level. There's lots of other things it does. Mathematics, we generate a mathematics from it. We generate algebra, we generate arithmetic. Entropy is encapsulated in the idea that the alphabet contains the previous one. That's something I didn't emphasize, but that's true. And entropy at each level is it's just the entropy is simply the order that we've reached, whatever that is. Yeah, and we can carry on with physics, but we do it in a different way, and but I don't want to go into that. And I found that genetics, because I worked with Vanessa Hill on that, and we got basically the same structure for genetics. And you can also do it in Platonic Solids. But this is what I like
Wait,
here.
wait, don't jump. What do you mean by Platonic Solids composed of two spaces?
Well, because each is a dual.
Each has a dual.
So you can imagine that's in another space. So you
Some
can
are self-dual.
yeah, some are, but cube and
But I
octahedron
see, you're
could be two
you make two
spaces.
spaces out of them in that
Yeah.
way.
Yeah,
Good.
and
And then there's the symmetry groups of them, which are deeply related to a lot of things.
oh, indeed. Once you've got things like that, you're
Yeah.
really shooting. And I think fivefold symmetry. This is fivefold symmetry. And this I thought looked like the monkey puzzle tree. And I've seen some visitors from the United States say, what the hell's that, when they first saw one. And I said, oh, that's very common in England, a monkey puzzle. They come originally from South America and were introduced into England in the 19th century, early 19th century. And there's tons of them about. This is a particularly beautiful example we saw a couple of days ago. So Sydney took this picture for me. And what I want you to see is that each divides into three, and then it divides into three again, then into three, forever. And this is what I think nature is doing. See, if you look at that's what you're doing. And that's your 5 parameters there. But it can be 5 at the next level and 5 at the next
So it's a
level.
five-fold fractal?
Yeah, I guess so. But you can, yes, it is basically a fractal. And you can replace, one space with another, so you can swap these round. That's your monkey puzzle tree.
So are we really not 5 fingers, but 3 fingers, and then 3 fingers?
Well, I use it for demonstrating this.
So we're fractally 3, not... Yeah, okay.
And we can do all kinds of tricks. I'm not going to discuss this too much. The double three-dimensionality can be seen as the crossover point is where you get particle. The crossover point between the two three-dimensionalities is your two spaces. And you can represent any system that conserves energy this way, because you can make it nilpotent. You can write an nilpotent equation for any of those. So any which does that.
Peter, so when you say also that the if the fermion is the intersection and crossover of these two double spaces, that's why you also don't need supersymmetric particles, because each particle is its own supersymmetric particle.
I need to think about that. I suppose that's true, because each particle in a vacuum is its own supersymmetry. Now you can have, because nilpotency creates a redundancy, you can sort of drop one of the three. Kind of. And you can draw that instead. And it's like something just simply branching out. These are conditions for generating Fibonacci numbers, as we saw. Quaternion is confined to the plane. Fibonacci numbers, or the golden ratio, emerge from even e squared minus p squared minus m squared. You can get the golden ratio from that, as I've found. And this is one of Lou's diagrams. I don't think it's correct, but well, Lou's diagram's correct. Lou's diagram's correct, but mine isn't. No, he's got the correct diagram. This is Heinz von Fuster's.
This is my version of
Yeah.
I am the observed relation between myself and observing myself.
Well, you see, you can also do a diagram like this for the rewrite structure eventually, because you can say every alphabet includes the previous one. And so you get something like that. And as I mentioned, the numbers used in everything, particle structure, genetic, Platonic solids, kissing numbers, major groups in particle physics, all are only based on 2 and 3. Even E8 and things. This is a way of deriving fundamental particles, and if you believe in the E8 structure,
No.
you can,
Go for it.
you can get 240.
Yeah.
And all those numbers you see, all the numbers on this table, you'll see reproduced somewhere in those things.
Peter, I think you just said it, the same thing my thought was, but there ought to be a mapping, if that E8 thing is right,
Yeah.
there ought to be a mapping from what you do here to the vectors in that E8 group lattice.
I think so. And I think this is it. And what you use is vacuum particles. But I think Garrett Lisi, didn't get the right connection. He only had 226. And he just said, oh, there must be 14 extra particles somewhere.
I think we have a,
So there's a project there to really actually look at that and figure out what the right mapping is.
I wouldn't go there.
You wouldn't go there.
I wouldn't go there. What the people know a little bit about this field, and what they call that whole thing is the desert. Because many people have gone in and no one's come out.
Well, anyway, regardless of that, I must mention Peter Marser because Mike wants me to mention him. I worked a lot with Peter Marser to explain systems at any level with this. And if you can crack any of Peter Marser's ideas, then that takes some doing. But
I've got
I
27
worked.
slides here which I can
Yeah, thank you.
do
Yeah.
that.
Peter, you're way out of time, which is
Okay.
great. Of course,
That's the end.
listen to you all day. So everyone, look, we're supposed to reconvene at 2, but what I suggest is we move it up a bit. We've got one talk which isn't going to happen this afternoon, I understand. Is that correct still?
Yeah.
So we have extra time. I suggest that we take some questions. Any questions?
Sorry, the gentleman.
So what do you think, this is where nature begins in a way, with this group structure, but do you have a sense of what it's trying to do with itself?
I think it's trying to zero itself, trying to cancel itself out to nothing. And it keeps doing it because each zero is a different one. And there was a quote from Spencer Brown about that, I think, wasn't there? Does anybody remember what that Spencer Brown quote?
Law of crossing, I mean, that sense of universe canceling itself out is, universe fits so perfectly into itself that there's no distinction.
Yeah, right.
Or since the nothing is so unstable, it could come apart a little.
They said the unstableness of nothing, that was
Yes.
the unstableness.
Yes, nothing is unstable.
Nothing is so unstable as nothing that.
It can only transform to nothing.
How does your nature fit in with category theory? In category theory, natural has a very distinct technical meaning. It means it's defined uniquely up to some level of isomorphism.
Right, you mean, I think that group of order 4 fits into category theory.
Yeah?
I think, as I say, that diagram is almost a category theory diagram.
Yes, it's got a jointness in it and
And I think that rewrite structure could fit into category theory if you stop it at 4.
Yes, well, it is over 4 levels,
Yeah.
category theory,
Yeah.
really. Yes, function, category, function.
Yeah, we intend to actually explore this aspect of
Yes,
category theory.
yes, I think it does look promising.
Yeah, Peter, I have 2 questions. The first is the set of iterations, as you use the term empty, therefore, the ones that are not in this model. Are there any iterations?
Well, the roles that I haven't done.
Do you have, are there observed characteristics of physics that aren't included in this? That's the first question.
Well, I can't think of many. There's not many. Yeah, not that I accept.
Yeah, okay, and then the second question is a kind of a follow-up, is, what the hell is the universe doing here? But did you attend Sahu's performance?
I did.
Dance, yeah. There's a laws of form pattern series of equations that he was acting through in an improvised way as he was doing this. So metaphorically speaking, I mean, is the universe in sort of conception in the rewrite algebra, is it just improvising forever through these rewrites, or is it like just choosing an equation at the beginning and running down?
No, I think it's improvising forever. I think the alphabet changes all the time, which makes it different from an ordinary computer algebra. Because computer algebra has a fixed syntax and so on, and this changes all the time. It rewrites itself all the time. And I think that's what changes in nature all around.
But is it developing in time?
Yeah, in time, in space, everything. Yeah, it's all the time. Yeah.
Oh, okay. Another relationship that we might look at is that recursive distinctioning model that I showed in the talk. That's a case where the alphabet is getting produced again and again,
Right.
rewritten. in terms of the distinctions that are being made. And of course, it's a very specific model, but it has that same idea.
Same idea of just generating itself forever and ever and ever.
Right.
So how does it know when to stop?
It doesn't stop. That's the
Things
point.
do, but you know, we stopped.
Yeah, but we are not the whole alphabet. We're only part of it.
Yeah, okay.
We're only a component. Yeah.
Continues.
Yeah.
The time kind of accumulate a sort of new level of wholeness.
But I don't know about time, but this alphabet can be started at any point in the procedure. It doesn't have to start right at the beginning. It doesn't have to start at the particle level. That's what I'm trying to say at the end. In fact, it can be applied at any level.
Yeah, but the wholeness must be
The
there.
wholeness is
Must be there for all time.
Yeah.
It is.
how things keep coming back into the whole.
Yeah, how they keep coming back into the whole. And if you're talking about consciousness, for example, I think, why are we conscious? What is it? I think consciousness is because we have evolved out of the connection with the rest of the universe.
Yeah, which is what John always
Yeah,
says.
and which is why we can perceive it. Because if we didn't, if we were just, created in some lab, that wouldn't be out of the rest of the universe in the same way, with a complete connection with it.
So, what would you, so David Bowen's got the idea of infinite order. Do you have a corresponding?
You'd better describe
So
that again. I keep forgetting what that means.
Shall I do it?
Yeah, go on.
Okay.
Yeah.
The implicate order is
It's like some place out of which the physics and the mind and everything would come.
Well, I think that could be the rewrite structure as a kind of implicate order, if you want.
Yeah. An originating symmetry. Is that it?
It is symmetry, but it's not. It's the rewrite structure
it's
that.
the way that something follows from something else. So it comes before time, but it is like time in the sense that it is
Yes.
ordered. So the implicate order of things is the way that X leads to Y leads to Z.
Yeah.
The thing evolves.
But Peter's got a structure, hasn't he?
Yes, he has, and that structure is something which has an evolving form.
Yeah.
But not the completed form only appears if you look at the universe, let's say four-dimensionally,
Yeah.
as a whole, as something which is rigid in space and time. This is one of the ways that Einstein thought about things later in his life. And then you have a completed thing which is now, has always been, and will always be complete, in the sense that time is just a dimension. But the ordering of that is coming from the implicate order according to Bowen. So,
Yeah, no, it's kind of
begins to
knock-
make
knock- it knocks you out.
No, so that book knocked me out as well. That's a beautiful idea.
Yeah.
Long time ago, though. Yeah.
What's the Bateson, Gregory Bateson? Is that meta system or a kind of? He had some idea of something, not implicate order, but something else.
Basin.
I can't remember what it was.
Relationship between the middle level and the level.
Yeah, something like that. Yeah.
What was important for Bateson was the difference that makes a difference.
Yeah.
Right.
Yes, the difference is the action, is the thing. Is this the same Bateman? Is this Bateman?
Bateson.
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 Yes, okay.
Yeah.
Right, good.
Yeah. Is that Bateson's son actually? Because his father was a geneticist.
Yeah, no, it's William Basin.
Yeah.
William Basin was the father.
Anyway, we're at 1:15.
So what time
yeah,
are we
another
coming
question.
I had a question about the Robinson non-standard analysis.
Oh, yes.
Did you have to find that in order to proceed with?
I knew something must exist which did what I wanted, but I hadn't a clue. And I kept getting a few hints from reading this and that and the other. And then I hit upon it. I don't know how I found it, but I hit upon it by keep reading. I then discovered the Robinson non-standard analysis and said, this is what I want. And also, one of the interesting things, I also was interested in something else, something that's related to that. I can't remember what topos theory. Yeah, and those were actually nilpotent in this. The space was actually described by nilpotents.
I think that nilpotent thing is absolutely essential, and I think this is why you should go nowhere near E8. Because E8 is a division algebra, it's a set of all division algebras. It doesn't
No,
have
but
to-
it's only for particles.
I know,
also.
but it's not the right basis. We can
No,
discuss
the
this.
right basis is fivefold.
Yes,
But
better.
but E8 has fivefold in it.
Yeah, but EA's got everything in it except for relativity.
It's got
It doesn't
relativity.
have, no,
I'd say it has.
no.
So when you mentioned non-standard analysis a moment ago, you were talking about the algebraic geometry kind with nilpotent infinitesimals.
Well, that was
Or
a
at least
later.
one should mention that.
Yeah, that was a later development that I found out about. I didn't know about the nilpotent infinitesimals at first, but I did know about the non-standard analysis before I knew about them.
But you had a glimmer about non-standard analysis being relevant?
Yeah, that something must be relevant. That did what I wanted.
Oh, I see, yeah.
Before I found out what it was.
It's very clear that it's relevant
Yeah.
if you look at it in the frame of the nilpotent infinitesimals.
Yeah, yeah.
Then it's as though, the nilpotents are down there in the depths of the space. They're
This is
there
the-
everywhere.
And it's the only thing that gives an interaction. If you have a nilpotent infinitesimal, that becomes infinite, and that gives rise to things that can
And then
interact.
that's what any kind of parallel translation means. It just means you're going by some nilpotent interaction.
But if a theory forces you to come up with an idea and you find that that idea is true,
Yes.
you know, then you really feel confident.
It's looking very, very good, a lot of this. If I can find, well, I hope we can find a way together to put all of this stuff together. I think it's a very, very powerful process.
And there's another category theory connection with the 5 and pentagon. There's the Saunders and MacLean, there's a pentagon coherence condition, but it talks about like non-associativity, and so I think that's sort of a very fundamental structure that comes out of you assuming using tensors. MacLean.
Coherence relations
and I'm wondering if that has something to do with.
Well, I'm not familiar with it, so I don't know.
I want to know that. Is there a single reference or a reference?
I just found a
I can get
couple of
you a
slides
reference.
from Peter
Great,
Hines.
love that.
But yeah, I don't know.
That's
But,
interesting.
so where are you thinking about that?
I don't know. I was just thinking about. It just looked like a very fundamental structure in terms of pentagon and 5.
Yeah, pentagon and 5 comes into it.
And then that comes into.
I mean, we did the biology that way as well. I mean, if you take the 64 codons, you can represent them using this algebra. And if you do, you get everything in groups of codons that produce particular amino acids. You can do it quite easily. You have one of the bases is represented by one ijk quaternion, one is represented by one ijk vector, and the other one's represented by 1 minus 1 I and minus I. And you get fantastic structure for it. But then you can also do it using the Platonic Solids, which we also did. And you'll see why the axis of DNA has got this pentagonal symmetry.
This pentagonal relation comes up in the following way. I'm just going to say it mathematically, but you may even see the relation. If you have a product of 5 things, and you have associated it, and you're in a non-associative situation, then you will see that you can reassociate. Now, reassociate means like somewhere in there you have AB times C, and you replace it by A times BC. Yeah? But inside the larger expression, then you find that there are 2 reassociations that go this way, and there are 3 reassociations that go this way, and you end up on the same point. So suppose that the simplest non-associative situation would be that if you go this way by 2 and this way by 3, you would get to the same result. And so that's called the pentagonal relation.
And that diagram commutes as well.
It's sort of not quite, it's sort of intermediate associativity, then you have an associativity, which is bidirectional, and binumerate.
You call this a coherence condition?
Not me.
Interesting.
And the category theorists came to this because they were thinking about tensor products, structures that weren't associative.
Right.
Interesting. So there's some literature on this, and obviously, is there a book?
I mean,
I can find a reference.
Thanks.
Also, there would be a wiki article on
So,
this. Coherence conditions.
This set of 5s for the codons could be represented on an icosahedron. And you get each of the there were groups of three and there were two others, and on the five edges of each pentagon on it, on the dodecahedron, icosahedron. And you could arrange it so that there were nilpotent structures. Nilpotent fives. And we've done that in a paper for VJ. It was a VJ paper. There's a VJ paper.
Tensor products appear under vector spaces, more in category theory, vector spaces, and that is the ring category, including the abelian properties, and that the best source for that is Peter Fried. F-R-E-Y-D. Fried did a lot of work on the ring and vector spaces. Fried argues it's quite similar to the work we do with topos and more conventional mathematics. It's just got a different initial object. But that's what Peter Fried said, and what he says is simple. It's actually often very far from that for ordinary people.
The problem is simple isn't easy.
What?
Simple isn't easy.
No.
Making it more simple is very difficult.
And what did Oscar Wilde say? Somebody said, I want the truth pure and simple. He said, truth is rarely pure and never simple. But simple isn't easy. It's the very opposite of easy.
Yeah, that's right.
It's very hard to think simply.
Exactly.
Ladies and gentlemen, we're at 1:20, which I'm absolutely happy with. Should we just make it an hour later and have another 10 minutes of discussion? Of course, it's going so well.
Well, I think...
Should we just move everything up half an hour? Shall we?
Yeah.
Okay, good. So we've got another 10 minutes. Great.
Yeah.
Good. Any more questions? Any more discussion on this? This is going in very interesting directions.
Oh, actually,
Or is everybody
there's
getting
another
hungry?
thing with the square. It kind of reminds me of squares of opposition in Aristotle.
Oh, okay, yeah.
And I don't know if you know the summer school logic, language, and information. They have like an S league every year. So one of the people, they work with diagrams, just starting off with the Aristotelian syllogism, but they start building these Platonic, like these solids and just diagrammatic relationships. I don't know if that could be interesting.
Well, it could be, yes, certainly. But the Vanessa and I made lots of models and things for what we were doing in biology. And conceptual models and actual models with these damn things. And she was much better at the art side of it than I was, so I let her do most of the diagrams, but you know...
Who's this?
Vanessa Hill, my colleague in biology.
Yeah, she's still about.
Yeah, she's still about. She's still in the London area, in